Do you ever find yourself not having the right IC for a project? And if so, would you like to learn how to program your own integrated circuits? If so, watch this video.
Hello, I am the Mighty Pez, and in this video I will show you how to program your own logic ICs using programmable logic devices or PLDs. So please, join me.
What is the difference between a programmable logic device or PLD and a normal static integrated circuit? Well, on a normal static integrated circuit, such as this OR gate or this 4-bit adder, its programming will never change. This IC will always be a 4-bit adder. However, a programmable logic device is configurable. If in one project you need an AND gate, an OR gate, a counter, or multiple functions all merged into one IC, you can use a programmable logic device. So in some cases, a PLD can replace an IC that you don't have in your inventory, and in other cases, it can be used to combine multiple functions and reduce chip count. A PLD is the predecessor to the modern FPGA, or Field Programmable Gate Array. FPGAs are just much more advanced versions of the old PLD. They're configurable like a PLD, but have many more gates and input pins, and are quite a bit faster, and in many cases can replicate an entire CPU.
For any demonstration project, I first need to identify a good use case function to implement as a PLD. In my case, I wanted an IC to drive a hexadecimal LED display. These are very hard to find, and I previously tried to purchase old stock MC14495 LED driver ICs, but unfortunately was sold fake chips, which is a story for another video. This example logic will take 4-bit inputs and produce a 7-bit output pattern to drive the proper LED segments. This function requires no state and therefore is purely a combinatorial Boolean function, perfect for my learning. Adding state to the programmable device functions is achievable, but will be a task for a more advanced video. For the specific hardware, I will be using the Atmel ATF22v10 PLD, chosen primarily because I have two in my inventory. There is a smaller pin count IC, the 16V8, that would have used less real estate, but the project is for my own learning and reduced pin count was not required. Next, we will take the 16 combinations of the 4 input pins and their desired outputs and create a truth table to define our expected results. The outputs of the truth table is 7 non-reduced functions, 1 for each of the output pins. Next, we will reduce the truth table for each function to return a simplified or reduced function. Why is simplifying the function important? To make sure the function is easier to understand and visually verify, as well as ensuring the minimal number of gates are used in the solution. As you can see in this non-reduced form, the function for driving segment A would be a lot more complex and require many more gates for the solution. Thankfully, there are websites for solving Carau maps online, as that would require an entire video to demonstrate performing that process by hand. The output of the Carau map process will be the functions needed for coding the solution using Atmel's very old application, WinCUPL. Caution, WinCUPL and PLDs in general are such old technology that you should be prepared for the application to be finicky. After successfully compiling, I will demonstrate the simulation feature before we commit the code to the PLD device. Lastly, we will program the device using the inexpensive and widely available TL866II Plus programmer, put the chip in our breadboard test circuit, and demonstrate the functionality.
Okay, in our first step, we are going to use a truth table to help us derive our Boolean function. And this is the spreadsheet that I've come up with to help us fill out our truth table. A couple items of note. The rows are the input values enumerated from 0 to 15. And I have labeled the column in reverse order, where D is the most significant bit and A is the least significant bit. When using the inputs, A will always be the 0 position, the 0 bit. The capital A through capital G are our outputs and represent the functions necessary to drive one LED segment. Over here, you'll notice the representation of an LED. It has 8 segments, including the period, which we are not going to use. So we're going to use 7 of the segments, A through G. So as we recall, a function takes one or more inputs, in this case 4 inputs, and produces one output result. In this case, it will be a 0 or 1 to represent true or false. Another item of note, this column over here labeled minterm is used to help us determine the minterm of each function. 0 through 15 is not the minterm until we match it up to the list of all ones, and you'll see what that means in a minute when we calculate the minterms. But in this case, it's just a list to help us determine what the minterm will be. To help us fill out this truth table, we are going to fill out one row at a time. So starting with 0, we're going to imagine this LED, what segments it would take to light the LED. And we know, in fact, it would take A, B, C, D, E, and F, but not G to produce the 0. So we'll go ahead and mark our row as such. Next, for the number 1, we will only need B and C. All other columns will be zeros. And we'll go ahead and do the obvious one, which is 8, which will light up all 7 segments. So let's go ahead and mark all 7 segments. And I will go ahead and fill out the rest of the rows. Now that our truth table is filled out, let's go ahead and use function A as an example to identify the minterms. So now we'll see the minterm is every value that generates a 1. So for function A, the minterms will be 0, 2, 3, 5, 6, 7, 8, 9, 10, 12, 14, and 15. And we'll go ahead and save this information to be used later.
A Carau map is a method of simplifying Boolean algebra expressions. They are used to simplify logic functions so that they can be implemented using the least number of logic gates. The Boolean results from the truth table that we created are transferred onto a two-dimensional array where each element represents the result for each unique combination of input. My first step is to reorder the inputs D, C, BA so that they are right to left and match up with the normal visual order of the 4 bits. This is not required as they are only variable labels and can be done in whatever order you find comfortable as long as you use the labels consistently from truth table through coding. Next, we will map the results of the truth table for each function separately. Please pay careful attention to the numerical ordering of the input names on both the rows and the columns of the map, as they do not increment 0001, 10, 11 as one might expect from binary counting, but rather increment 0001, 11, 10. I have entered the results of the truth table into a spreadsheet to guide us, and will now transfer the results of the function for segment A onto the map. Notice the minterms generated by entering the results directly onto the map are in fact the same as the ones generated by hand. This is our validation that we did enter the values correctly into the map. However, now that we understand this, we also have a shortcut and can enter the derived minterms directly into this field to populate the map, saving time and making the entry less error prone. We will take the resulting Verilog solution for our Boolean function and save it. We chose the Verilog form as it is closest to the CUPL form that we need, and will need only minor changes to suit our needs. I will now demonstrate our shortcut by entering the minterms for segment B. As we did for segment A, I just list each of the input values that result in segment B having a value of 1. As mentioned, there needs to be a little cleanup to get the Verilog form of the equation into the CUPL form. To demonstrate, I will paste the 2 functions already generated into Notepad. First, we will replace the tilde, which represents the Boolean not function, or inverse, with an exclamation. Next, we will replace the vertical pipe, which represents logical OR, with the pound sign. The logical AND does not need to be changed, as the ampersand is the character representation used in CUPL. I will paste the resulting changes back into the spreadsheet. Then, I will go ahead and perform the remaining calculations in preparation for our next step. The next step of this project is to take the logic as defined by the truth table and convert it into the programming for the IC. So for that, we're going to use a program called WinCUPL. So we're going to start with a new project. It's going to ask us several questions. Name of the project, what the current date is, your revision, doesn't matter what you choose here, the designer, so after we create the project, we will look up the proper device code that we'll be using. It'll ask how many input pins there are and how many output pins. And again, we have 4 inputs, 4 bits, and 7 segments. And it will go ahead and create the basic outline of the program. As I mentioned, we're going to have to determine what device we're going to be programming for. So there are options, devices. So we know the device. It is an ATF22v10C. And according to this, the mnemonic is G22v10. So that's what we'll be using as we write our code. The device and the project name are the two most important fields in the project header. So I've already prepared the code and we're going to discuss it one section at a time. First is the header section. As we previously showed when we created a project, it fills in most of the fields. Again, the device that I'm using is a G22v10, which is the mnemonic for an ATF22v10C Atmel device. The next section will be the definitions for the input pins. As we can see, there are 4 inputs, A through D, A being the least significant bit, and D being the most significant bit. The output pins are represented by OA through OG, which represents output pin A or segment A through output pin G or segment G of the LED device. The last section will be the minimized Boolean functions that we defined using the Carau Map process. Now we're ready to compile our program. And it compiled successfully. In order to run a simulation of the PLD programming, we need to have an SI file or simulation input file created. We can do that one of two ways. We can enter the text directly into an editor, or you can use the simulation tool. In this case, I created the file directly in an editor. The SI file consists of 3 sections. The first, of course, is the header section, and it's the exact same code that is in the WinCUPL source code file. So we need to make sure we cut and paste the same header to make sure that the fields match up. The second section is the order. This will just tell us in what order we will be feeding inputs and expecting outputs from the simulation. You can see here that I arbitrarily ordered it DCBA, the 4 inputs that we'll be feeding into the simulation, and then OA through OG, which are the outputs that we'll be expecting from the simulation. After we define the order, we'll actually define the vectors. And we can do as few or as many as we want. In this case, I will be fully testing all inputs from 0 to 16 into the PLD simulation. We could just as easily pick the first 2 or 3 if we trusted that our functions work, but entering 16 inputs was not a big hardship. And from that, we will then generate the 7 outputs for each input in the simulation. From the menu options, we will choose Device Dependent Simulate, which will then bring up WinSim. From the WinSim menu, we will choose Simulate and Run Simulate. This will execute the simulation against our programming and provide the output map that we can then use to compare to our original truth table to see if we got the programming right.
We'll take a printed copy of the simulation output and do a quick comparison just to show that we did indeed get our programming right. So let's go ahead with the first number 0 And in this case, the row will be matched up to the column. So this will be the row for address 0. And we can see that, in fact, A, B, C, D, E, F are all high, and G is low. So our input for 0 worked. Now we'll try 1. And 1 should be low, followed by 2 highs, followed by 4 lows, which is indeed correct. So 2 is correct. And we'll go ahead and just check 8, which would be over here. So 8 should be all highs, and we'll go through OA, OB, OC, output D, OE, OF, OG, and sure enough, all outputs are high. So I will go ahead and verify all of the rest of the inputs, but at this point it looks like the programming is good.
The next step is to hook the TL866 programmer up to the PC and insert the IC for programming. Next, we'll fire up the XG Pro Programmer software. So we make sure that the correct IC is the selected IC. Then we're going to perform a read on the device to ensure that the device is connected and seated well in the socket. Next, we'll go ahead and pre-erase it, although this is also part of the programming step. I do it separately so I can read the IC and ensure that it is indeed clear. So we do a read after the erase, and we'll notice that it is now set to all ones. That's what we expect. So let's go ahead and load the JED file. This is the programming that we will apply to the IC. I'm going to go ahead and program, and I always make sure that the lock bit is not set so that I can go back later and read the IC. So we hit the program. I'm going to go back one last time and read the IC to ensure that the programming made it to the chip. As we can see, it is not all ones anymore, and it is indeed programmed correctly. We are now done with the programming step, and we can remove our IC and go put it into the test circuit for testing.
The circuit consists of a 74393 4-bit counter, which is used as an input to our PLD. The output drives the 7-segment LED seen here. Additionally, I have 2 buttons, one to reset the 4-bit counter and one to increment the 4-bit counter, and an LS18 debounce IC to prevent double counting when I push the button. So let's go ahead and test it out. Go ahead, hit the reset, sets it to 0, and now let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. Our circuit works, and it rolls back to 0.
Thank you for watching, and I hope this will give you a start on working with programmable logic devices in your next project.